So welcome to the lecture on programming, data analysis, and deep learning. Last week we have looked at an extension to a logistic regression and at multi-layer neural networks. And in particular, we looked at classifying movie reviews. So what we did is we went to the Internet Movie Database, and for a large number of movies, there we can find reviews where people said, oh, this was a brilliant movie, blah, blah, blah. And then what we try to do is we try to build and train a neural network that can classify whether a review of a movie is a positive or negative review. In order to do that, the first thing that we did is we took this review, which was a lot of text, this movie, blah, 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 blah. And then we assigned to each word, we put each of the words here in a dictionary. So maybe this word is 43 and this word is 521. And we had 10,000 words in the dictionary. And if there's a word in the review that's not in the dictionary, we just put a question mark there. And question mark is, I don't know, it's some special number. And what we did then is we took each of these reviews, which was a list of numbers. So it was a list of integers. And we converted each of these reviews into a giant vector. So each review becomes a gigantic vector where maybe some entry here is the word brilliant, and some other entry might be boring, and some other word might be exciting, and so on. And for each of this review, we turned it into a vector of zeros and ones, where a 1 means this word occurs in the review, maybe this word does not occur in the review, and this word also does not occur in the review. So each vector is a very long, each review is a very long vector of zeros and ones that just signals whether some word occurs in the review or doesn't occur in the review. And then we added 3 layers of neurons after that. So the first layer was a layer of neurons where each of the neurons is like a logistic regression unit, only that the activation function that we used is not the sigmoid function, but it's a ReLU function. And if you remember, the ReLU function was this function, which is flat for negative and slope of 1 for positive. And in particular, we had 16 units here, 16 ReLU units. And what we did is we fully connected each entry in this vector with each of these 16 units. So this unit gets input from every entry in this vector. And each of these connections has a weight. And then the same for all the others. So, and you can already see that there's a gigantic number of weights here in this connection, right? So here I think our dictionary we limited to 10,000 words. And here we had 16 ReLU units, so we have 16 times 10,000 weights in here. So by far the biggest number of weights goes into these connections here. And then after that, we added another layer of, again, 16 ReLU units. And also these were fully connected. So here we had 16 more ReLU units. And then we added one single unit in the end, which collected all these 16 inputs. And this single unit had a sigmoid activation function. So this is one sigmoid unit. So this last unit outputs a value between 0 and 1, where we said that I think everything below 0.5 was negative, and everything above 0.5 was positive. And the parameters of this network are all the weights here, all the biases, a bias for each neuron here, then all the weights here, a bias for each neuron here, and then all the weights here. These are not so many, these are just 16 weights, right? And one bias here. But by far the biggest number of parameters is here. And then we went through our, we downloaded a lot of pre-labeled examples from the database, and then we did gradient descent on all the weights and all the biases to adjust all these weights and biases, and then we tested this network on reviews that it hasn't seen before. And I think the accuracy was pretty good. I think the accuracy was on the test set, so accuracy on reviews that the network has never seen before was 85%. So if we give this network a review of a movie, and this network has never seen that review before, then with 85% accuracy it can detect whether it's a positive or a negative review. Any questions so far on this movie classification? Yes? Okay, so the question is, how many neurons do you put in each layer? And actually there's a second question, how many layers do you put? And unfortunately, there's no good guidelines for that. So what you have to do is you have to train a lot of neural networks, you have to try different things, and then you have to develop some intuition. And if you have a good intuition, then you call Google or Amazon and you tell them, okay, I want to work here for you, I want to earn more than 1 million per year, but I have a very good intuition on choosing how many neurons to put on each layer and how many layers to put. So this is the way that it works right now, that there's just people who have a very good intuition on what to try, but in general there's no good guidelines. So in general, you try different things. I think one recommendation is to start small, and then to keep adding neurons and keep adding layers until you get overfitting. So you observe the effect on the validation data set. So you increase the network size until you clearly see some overfitting, and then you use some regularization techniques that we will see today or tomorrow on dealing with the overfitting. But the idea is to start with something small and then to increase until you get overfitting. One guideline is also if you have multiple output neurons, then one guideline is that the intermediate layers should not have less neurons than you have in the output layer. So if you have 10 neurons in the output layer, then you should generally avoid to have intermediate layers with less than 10 neurons, because you might create some information bottleneck and lose information. Yes?
You just said tomorrow?
No, next lecture, sorry. Yeah, there's nothing tomorrow. Yes? Yeah, so that's the problem. So the comment was that if you don't have a lot of data, you will easily get overfitting, right? And one way to deal with overfitting is not to have too many parameters in your model, not to have too many neurons. So in general, if you have more data, you can afford to create a more complex model because you have this huge amount of data to create this large number of parameters. So this is why companies spend a lot of money on getting more data. And this is also the reason why Facebook and Google provide nice services for you for free, because they get data from you, right? So and from that data, they can train their neural networks much better. Okay, so what we can learn from the last example is that actually a lot of the programming work, so building and training the neural network is just like 5 lines of code, right? And most of the code goes into preparing the data set. So most of the work actually goes into some pandas like stuff like slicing and dicing data sets and cleaning up data sets and preparing everything for learning. And then building and training the neural network, that's only a very small part of your program. Then in general, these stacks of dense layer means fully connected, right? Everything is connected to everything else. And multiple layers of densely collected ReLU layers, neurons with ReLU activation functions will generally work quite well. So I think if you don't know what to do, use a dense layer with a ReLU activation function. That's generally often a good guideline. Yes?
When experimenting in the exercise, we also tried pushing up ReLU and softmax, for example, and we did notice some difference, but we couldn't actually describe where the difference was. Is there, in practical use, an essence to this difference?
Did you use softmax in the last layer or in hidden layers? Okay. In generally, I think I've never seen anybody using softmax in hidden layers. So in my opinion, I mean, I'm not a deep learning expert, but I've only seen softmax in the last layer. I think we've discussed about softmax last time. It's if you have multiple final neurons and you want them to output a probability distribution, so you really want them to sum to 1 and to have each of them to have a value between 0 and 1, then you use softmax. But for the hidden layers, you usually don't care whether they sum to 1 or whether the values are between 0 and 1, right? So in the hidden layers, I would generally always use ReLU. Some people use sigmoid or tangent hyperbolicus. In the past, like 10, 20 years ago, people used to use tangent 10H here. But I think nowadays in the hidden layers, almost everybody only uses ReLU in hidden layers. And then the choice of more fancy activation functions is mostly for the last layer to make the output of the neural network fit fit your data. But maybe there's something interesting. Maybe nobody tried that using softmax in hidden layers. Maybe it's good. Maybe you can write a paper about that. I don't know. But in general, I think it's not very common. Okay, so if you have binary classification, then your last layer obviously has to be only one neuron with the sigmoid activation function, right? So you have one value between 0 and 1. And then you can have some binary classification. And the loss function for binary classification, the best one is the one that we have used so far. This is this binary cross-entropy loss, the one that we also used with logistic regression. Then for the optimization algorithm, we've only been using RMS-prop. And there are tons of other optimization algorithms, like Adam and so on. But what I've seen people recommending is experiment with the other things, but always use RMS-prop. So usually, I think some people recommend there's not a lot of gains in using other optimization algorithms. And if you just go for RMS-prop, it's probably stick with RMS-prop, tune all the other parameters, And this is called hyperparameter tuning, right? How many neurons, how many layers, and so on. And maybe in the end you can try different optimizers, but I've seen people recommending a stick for this. And then, of course, beware of overfitting. So you should always have a validation set so you can see whether you're overfitting or not. If you don't have a validation set, then there's no way that you can see that you're overfitting, right? So in general, what you should do is, if you have some data, so say if this is your data that you have, then the general recommendation is to take a big chunk of that for training. And to use some of it for validation, and some of it for final test. Can anybody say why we need a separate validation and test set? Or what's the does anybody know what's the different roles of validation and test sets? Yes?
I think that validation is to check during the process of optimization how well you're doing, while the test is just an ex post kind of thing.
Yeah, so the general recommendation is don't look at the test set, right? Hide the test set. The test set is something that you hide away in some safe, and you make sure that nobody can peek at it, right? Because the test set is what you use only at the very end to get a good estimate on how well your neural network will do on some data that it has never seen, right? And the validation set, this is what you use for hyperparameter tuning. So you train the neural network, you validate it on the validation set, you see how well it does on the validation set, and then you tune all the hyperparameters. Tuning. Can anybody propose some hyperparameters? I think some questions we already had. How many neurons per layer? Some other things that you want to tune, yes?
Using RMSProp, we could tune step size.
Yeah. Learning rate?
Yeah.
Yeah.
Also on RMSProp, there was this rule, although I cannot explain it right now.
I think probably I didn't bring that. RMSProp. Does anybody know what row does in RMSProp? I mean, in RMSProp we had this weight algorithm, so the weight update, I think this is what we called alpha last time. No, what we called beta last time, probably. I don't know what row is in your implementation, but in RMSProp we had this SDW is beta times the previous SDW plus 1 minus beta DJ DW squared. And then the weight update was W is W minus alpha times 1 divided by square root of this S dW partial J partial W. So I think this is the learning rate. So probably the other parameter is this one up here. but maybe there's some other parameters in that implementation. Yes?
In the KRS documentation, it's recommended to leave every parameter as its default
Except, okay, they say only tune the learning rate, right? Don't tune the others. Okay. Some other hyperparameters that you can tune. One obvious one, yes? Number of layers, yeah. Okay, and then there's obvious, yes? Batch size, yeah. I will explain a bit later today what exactly the batch size does. Number of epochs, yeah. And then there's optimizer and so on. Optimizer, regularization, and so on. Maybe I add regularization later. Okay. So basically, you tune all these parameters and you observe the effect on the validation set, right? So again, why do we need a separate test set from the validation set? Yes? Yeah, exactly. So if we keep on tuning these hyperparameters, we might start overfitting on this validation set manually, right? We might start tuning all these parameters so that it works perfectly on this validation set, but then we are not sure how well the entire thing will do on some data that we have never seen, right? So basically, information from the validation set leaks into the hyperparameters, right? So the performance on the validation set afterwards is not a good estimate on how well the network will do on some other new data. So what some people do in companies is they don't have a test set, right? So the test set you only need if you really want to know how well your network will do on some unseen data. So it's like in the very end, when you're done, how good is it really? If you don't care about knowing how good your network really is, then you don't need the test set, right? You just try to build a good network using the training and validation set, and then you can never be sure how good it really is on new data, but maybe you're fine with that, right? Maybe you're just trying to build a good network. Unfortunately, in some companies, or a lot of people, if they don't have a test set, they only have a training set and a validation set, then what they say is that they have a training set and they have a test set. You just need to know, if you talk to them, you should tell them, oh no, you don't have a training set and you have a test set, you have a training set and you have a validation set and you don't have a test set. Right? So your performance on your validation set is not a good estimate on, if you go out to the real world, how well it will really do. Okay, so maybe you want a test set, maybe you don't want a test set, it's okay. You always need a validation set, but the performance on the validation set is not necessarily a good estimate on how well your algorithm will do in the real world or on the test set. Okay. And in the past, what people did like 20 years ago, I think they had something like maybe 70%, 15%. But nobody's doing that anymore. Because if you have a gigantic data set with like millions of examples, there's no way that you need 15% of that, of a million, for validation, right? So if you have a gigantic data set, then most people would go to 99.9% or something, and this is 0.05% and 0.05%. So generally, I think for the validation set and the test set, you should just make sure that there's absolutely okay number of examples in that. maybe there should be like 10,000 examples or so. And if you have a gigantic data set, then you don't need to, I mean, if you only have 100 examples, right, then you definitely need more here and here. Or if you only have 1,000 examples. But if you have 10 million examples, then you can have much smaller validation and test sets. Okay. Any more questions so far? Okay, then let's go at the next example. So what we want to do today is we want to do a multi-class classification. So what we did last week is we had binary classification, right? We only had 2 categories, good or bad. But the week before, also last week with the handwritten numbers, we had 10 different classes, right? So I want to show you another example, what you do if you have multiple classes. Okay, and we will look at the Reuters data set. Does anybody know the Reuters? Does anybody know the Reuters news agency? They send like short texts, like I don't know. Maybe they send. Oh, Shell found a new oil field in I don't know somewhere. The Reuters data set has these historical text. Maybe blah blah blah. Some company increased their I don't know, or somebody Shell bought some other oil company or something. So they have a text, and then they have I think 40 something categories. So they have different categories, and the categories are whether it's about cacao. Vegetable oil, then they have different things, whether it's about wheat, and so on, right? So there's quite funny categories. There's also a category that's called rubber, and jobs, and so on. What the data set has, it has all these texts, and then it has associated one of these, I think, 46 or so categories. 46 categories, whether it's about cacao or vegetable oil or wheat or something else. Okay, let's load the data set. Data set is in Keras. So from TensorFlow.keras datasets, import Reuters. And then we need NumPy, import NumPy SNP from TensorFlow Keras, import models, and from TensorFlow Keras, import layers, and matplotlib, import matplotlib pyplot as plt. Okay, I think that's all we need. Then let's load the training data and the test data. So train data, train labels, and test data, test labels as Reuters load data. And then we have to specify the dictionary size. And we go for 10,000 words in the dictionary. Then train data. Okay, so in the training data we have 8,900 Reuters. I think they're called cables or something, or these texts from Reuters. Okay, so we have 8,900 of these texts. In the test data, we have 2,200. This is one case where the data set is not gigantic, right? So we need a bit bigger test data and bit bigger validation data. Okay, and then let's look at one of these texts. Print train data. Oh, maybe this one? Okay, this is one of the texts. So word 1, word 245, word 273, and so on. They're called newswires. Yeah. Okay, and then let's look at the train label. Train labels 10. Okay, this is category. This text here is category 3. I don't have any idea what category 3 is, but maybe it's cacao. Okay, so the first thing that we will do is we will do the exact same thing as last week, and we will turn all these lists into these vectors of zeros and ones. Def vectorize. I think they're, what's that called? News cables or news wires? News wires. News wires. Dict size is 10,000. So we will generate a matrix. Results is NP zeros. We initialize the matrix with zeros, with len news wires. So now the rows are the news wires and the columns are the words. Dict size. And then we iterate for news wire index word list in enumerate and news wires. So we iterate over all the news wires, and then for word in word list results. So the news wire index 0 and the column is the word. We set that to 1. Return results. So we generate this gigantic matrix. So X train is vectorize news wires train data, and X test is vectorize news wires test data. Oops. News vectorizes. Oh, vectorizes. Okay, thanks. Okay, and then we need also the labels. The categories now is, maybe it's category 3 is vegetable oil. And what we will do is we will convert that to one hot encoding. So the number 3 will be converted to a gigantic vector from 1 to 46 entries, where we have 0, 0, 1, and all the others are zeros, right? This is one hot encoding. We have a 1 representing this category. So there's this function in Keras from TensorFlow Keras utils import to categorical. One hot train labels is to categorical train labels, and one hot test labels is to categorical test labels. Okay. Maybe we can look at one of them. One hot train labels shape. Okay, so it's the rows are now the examples, and the columns are all 0 or 1. So if we look at the first review, I should probably print that so it goes into a row. Okay, so this is now the representation of the label. I think the first example is category 4, probably. So this is category 1, 2, 3, 4, and 4 has a 1. Train, no, it's category 3, so we start counting at 0. No, train, labels, 0. That's category 3. So this is category 0, 1, 2, 3, and 3 gets the 1. All the others are 0. Okay. Now let's go for the constructing the model. Model is models sequential. Okay. So we will go for dense ReLU layers as always because we know them, we like them. Let's stick for dense ReLU layers. Model add layers dense. Okay, and now the question is, how many neurons in that layer? Can anybody propose something? How many neurons should our layer have? Yes? More than 46. Yeah, that's a very good idea because our last layer will have 46 neurons, right? Because we have 46 different categories. So it will be a very good idea to have our hidden layers not have less than 46 neurons. Otherwise, we might create an information bottleneck, and the hidden layers might lose information that might be necessary later in the last layer. Okay, and I think let's go for a power of 2, 64. It's always good to go for powers of 2. I think it's good for memory reasons, right? Because all the memories might be a cache and so on, might be a bit faster if you go for powers of 2. Okay, activation will be ReLU. Activation is ReLU. Input shape. Can anybody propose an input shape? How big is the input layer? Yeah. 10,000, exactly. Because there's 10,000 words in our dictionary, right? And each word can be either 0 or 1, so there's 10,000, our input layer is a 10,000 element vector. Okay. Then let's add another hidden layer. Model add layers dense 6 same shape. Activation ReLU. And then let's add our last layer, model add layers dense. Okay, how many units in our last layer? 46, because there's 46 different categories, right? Activation. What activation function in our last layer? Softmax, exactly. Softmax, because we want to predict like a probability distribution over the different labels. So all the units in the last layer should sum to 1, and each of them should be between 0 and 1. So we use softmax. Okay. So let's compile the model.compile. Let's stick for RMS-prop, no experimentation with the optimizer. What loss function? Yes? Exactly, categorical cross entropy, because it's like the cross entropy loss that we used before, right? The binary cross entropy loss was the one that we used with the logistic regression, but now we have multiple categories, so we need to extend that to categorical cross entropy. Okay, let's save our metrics. And let's go for accuracy. Let's just save the accuracy. Okay. Now let's set aside a validation set. X validation set is X train. Oops. Let's put the first 1,000 examples as a validation set. This what I'm doing here is actually, it's a bit dangerous. I'm just picking the first 1,000 examples for the validation set. Why is that maybe not smart? Yes?
Case data is ordered.
Yeah.
We pick all the positives.
Yeah.
So we can predict on the negatives.
Yeah. Exactly. If they are sorted, right, in the data set, then it's very dangerous to just pick, maybe they are sorted by the category, right? So we pick all the cacao examples as validation set, and then for training we use the vegetable oil, wheat, and rubber, right? And obviously that's not, so we need to shuffle the data set. I hope this data set is pre-shuffled. Let's hope it's pre-shuffled, it's not sorted. And let's just pick the first 1,000 examples for validation. And then the remaining data, training data, partial X train as X train. Okay, the remaining. Okay, and the same for the validation. Y val is Y train. Oh, no, it's one hot train labels. One hot train labels. Okay, for validation, I'll pick the first 1,000 and partial Y train is one hot train labels, the remaining ones. Okay, now let's do gradient descent. Let's store the history so we can look at what's going on. So this history object will save how the training loss and the validation loss developed over time. And now let's say model.fit training data, partial X train, partial Y train. How many epochs? Can anybody propose how many epochs we should train? This is something that you generally have to experiment with, right? What did you previously use in the exercises? Like a rule of thumb? Yeah?
Between 10 and 40.
Yeah, between 10 and 40. Let's go for 20, just randomly. Epochs, 20. Batch size. I'll explain in a moment something about batch size. And then we have the validation data. Validation data is X val and Y val. Okay, and now, if I now press enter, you should pay attention that if you look at the URL up here, I'm not on my laptop. So everything that I've been programming so far was not on my laptop, right? This Jupyter notebook is hosted on our server in our offices over there, which has a very big graphics card. So it has more than 4,000 cores on the graphics card. This is why this training will go much faster than if you try to do that on the laptop, on your laptop. Okay, let's go for, oh no. Validation data, I forgot this equals, so. Okay, so this is going blazingly fast. Oh, it's already done, right? Okay, let's look at the accuracy. So the validation accuracy that it finally achieved was 80%. But in between, there seems to have been some higher accuracy. So after a few iterations here in the 11th epoch, it had 82.5%. So it seems that we got some overfitting down here. And obviously, the accuracy on the test data is much higher. It's 95.8% at the end. But let's plot that. Let's look at the loss values from the training data. They are in this history loss and loss. So validation loss is in history validation loss. PLT plot loss values label training loss. Okay, and then maybe in the same plot we PLT plot loss values label equals validation loss, and let's go for legend. PLT legend. Okay, so you see that the training loss goes down at every iteration. That's nice. If the training loss doesn't go down over time, we have a problem, right? Because it should get better, because we're doing gradient descent after all. But the validation loss goes down in the beginning, and then it seems to like have its lowest points here, and then it seems to go up again. So it seems that back here we are starting to overfit. We can also plot, if we want, we can plot the accuracy. Let's plot the accuracy. Let me copy this. Oh, and we also need this. Okay, so let's plot the accuracy. Validation accuracy. So okay, let's plot that. The accuracy values and the validation accuracy values with this is the accuracy, and this is also accuracy. Okay, so the accuracy goes down for the training data from 55% correctly recognized category to over 95%. But for the validation data, it seems to peak at somewhere like 80% accuracy, which is not bad, right? I mean, there's 46 different categories, and in 80% of the cases, our network can predict the correct category for these newswires. I think it's pretty good. Then we can also look at the absolute numbers. We can say results is model.evaluate on the test data on hot test labels. So now what we could do is we could start tuning all the hyperparameters before we finally evaluate it on the test data. Then we evaluate it at the very end on the test data, and we create some Okay, so this is the final loss on the test data, and the accuracy on the test data is 78%. Right? Because we didn't do any hyperparameter tuning, obviously the accuracy on the validation data is very similar to the test data. Maybe we can look at one of these. Maybe we can predict one example. Predictions as, let's predict all the test data. Model.predict X test. And now let's look at one of them. Predictions 0. Okay, so the first newswire, the network is really pretty sure that it's this category, I don't know what it is, 3, I think. And it's pretty sure, so it outputs 0 for almost all the categories, except for, maybe we should plot like this. Okay, so it outputs almost 0 for almost all the categories except this one category. It outputs almost 1. Funnily, interestingly, this category has a slightly higher value. It's just a little bit higher than 0, but it's still very close to 0. So, what we can learn for this, if we have n classes, if we do categorical classification and we have n different classes, then obviously our last layer, if we use one hot encoding, should have n neurons, right? And the last layer, also if we do classification, you should generally use softmax as an activation function. And the best loss function, if you do multiple categories, is a categorical cross-entropy. And also this one hot encoding is quite good. If you have multiple classes like this, then usually this one hot encoding works quite well. Another possibility is to have output an integer at the very end as a category. But generally, I think I could recommend you to use one hot encoding. And generally, I think you should avoid intermediate layers that are smaller than the final layer. So if your final layer has 46 neurons, then your hidden layers should not have less than 46 neurons. Maybe you can play a bit with that and try to have a hidden layer with only 3 or 4 neurons in here, and you will see that the accuracy goes down quite a bit if you have a very small hidden layer. Because even if the stack is very deep, if you have a lot of layers, if there's a single layer that only has very few neurons, right, then all the information has to go through that layer. So every layer can create an information bottleneck. Right. So if you have only a single small layer, you will lose a lot of information in that layer that's too small. Okay, then in here, the one parameter that I didn't really explain was this batch size, which we have here. So here the batch size, we have to specify in the fitting, we have to specify the number of epochs and the batch size. And with the gradient descent algorithm that we currently used for logistic regression, there was not really an epoch and there was no batch size, right? So I want to quickly explain how that works. So in our gradient descent algorithm, we had this weight update where W was equal to W minus the learning rate times the cost function, the gradient of the cost, which was just 1 divided by the number of training examples times the sum over all the training examples. So if T is the training set, with M examples, then we summed over all examples from this training set of the gradient, or the partial derivative of the loss of that training example. That worked very well for our logistic regression. What's the problem here if our training set is gigantic? If we have a very, very large training set, why is this problematic? Yes?
You will have to
Yeah. Before we make a single step of the weights, we have to evaluate the loss function for each example in our data set, right, in our training set. And if our training set is gigantic, this will take forever, right? So it will take a very long time just to make a very small step on our weight set, updates. And if we think about what we are doing, why we are doing that, is that so let's say we have two weights, W1 and W2, and our cost function looks something like this. So maybe the minimum is here, and then the cost function is here, like this, and we randomly initialize W1 and W2. So it's very important to initialize these parameters randomly. And maybe the initialization is here. Then what we are doing here by determining or by calculating the loss for all the training examples and calculating the derivative of the entire cost perfectly is to find the perfect direction in which we want to go, right? So this is really about finding exactly the angle in which we want to go before we make a single step in that direction. And finding this perfect direction in which we want to go takes a very, very long time. So I think one obvious idea is to say, oh, maybe we don't need the perfect direction in which we want to go. Maybe we just need an approximate direction in which we need to go. If we can find a good direction very quickly, why would we spend like tons of time to find the perfect direction, right? And that's the idea behind a stochastic gradient descent. The idea behind a stochastic gradient descent is not to evaluate all the training examples to find the perfect direction, so stochastic gradient descent just evaluates a single training example to find an okay direction in which to go, but which is very fast to evaluate. So with stochastic gradient descent, we just evaluate this for a single training example, and we just say that W equals W minus alpha times just one training example. The derivative of the loss for some training example. Loss W, I don't know, some R for random, maybe. Y hat for random. So we just evaluate a single training example, and we go in that direction. And the effect that this might have is this single training example might take us into a completely wrong direction, right? But it's on the other hand, it's super fast to compute. And the general idea is if we take a lot of steps in maybe random directions, but generally in the direction towards the minimum, then maybe over time this will take us still to the minimum. And then it will jump around the minimum, obviously. So whereas with the full gradient descent, finding the perfect direction at every step will take us on the perfect path towards the minimum, but very slowly. It takes a lot of time for each step. The stochastic gradient descent takes us in the general direction of the minimum very quickly. However, this stochastic gradient descent has one very big disadvantage when it comes to graphics cards. Does anybody have an idea why this is super inefficient for graphics cards? So remember, our graphics card on the computer that we're working on has more than 4,000 computers that are working at the same time in parallel, right? So our graphics card has 4,000 something cores. More than 4,000 cores. And all of them can work in parallel, right? Yes.
So if we work in parallel, before we do a weight update, there always has to be this one computation, so all the cores have to wait until this one computation is done, and then we can do the next one.
Yeah. So we use almost all the speed up from our graphics card, right? From parallelization. So why only compute the loss function for a single training example and have all the other cores wait on the graphics card, when at the same time they could also simultaneously compute the loss for some other training examples, right? So this is, and that's the idea behind a mini batch gradient descent, or yeah, mini batch gradient descent. It's not to have our cores sitting idly, but to keep our cores busy, to keep to calculate the loss on a few more training examples simultaneously, to find a slightly better direction in which to go. Right. So here, what we do, we split our training data set into mini batches. And we call these mini batches BJ. BJ. This is mini batch number J with small b examples. So the batch size is B. So this B is now the batch size. And now the weight update is W minus the learning rate times, we calculate the cost function for our mini batch and go into that direction. So it's 1 divided by B sum over all the examples from our mini batch. D by dW of the loss of all the examples in this mini batch. Okay. So this mini batch gradient descent is something between stochastic gradient descent, where we just calculate for a single example, and full gradient descent, where we calculate the cost for all examples before we make a single step. And the effect of that is that it's almost as fast as the green line, but at each step goes into a much better direction, right? So it doesn't wander around as randomly as the green line. So it's still a bit random. But it takes us to the minimum very quickly. Okay, here the red one is full gradient descent, the completely random green one is stochastic gradient descent, and a mini batch gradient descent is the yellow one. So now the critical question is, how big should this batch be? How big should I make the mini batches? Does anybody have some suggestion? What about picking a mini batch size of 1? What would happen if I make the mini batch size 1? Yes? Yeah, it's just stochastic gradient descent, right? If the mini batch size is 1, then each mini batch is just a single example, and I end up at the stochastic gradient descent, which is kind of fast, but it doesn't pick very good directions, right? Because the examples might be different. What if the batch size is the full training set? Yes? yeah, then we are back to full gradient descent, which gives us a perfect direction towards the minimum, but might take a very long time to compute. So in general, the batch size should be somewhere between 1 and it definitely needs to be smaller than the training set size, right? But how big? Yes?
Somewhat less than the number of cores in the optimum case.
Yeah, the answer is it depends on the graphics card, right? It depends on the number of cores on the graphics card, it depends on the memory on the graphics card, so that our examples fit all in the cache memory and we don't have to copy stuff back and forth and so on. So the answer is the optimal batch size depends on your data set and it depends on your graphics card, and it's very hard to know in advance, right? I think nobody knows a good formula on how to compute the optimum batch size. So you have to play around with that. And some guidelines for good batch sizes. So some guidelines for good batch sizes is if the training set is small, if the training set is smaller than 2000, if M was the number of training examples smaller than 2000, just do a full gradient descent. Just make batch size, I think I called the batch size B. B. Just pick a batch size equal to the number of training examples. Because your training set is small, it doesn't matter, right? You can do full gradient descent. You shouldn't bother with some mini batch gradient descent. Else, it depends on your graphics card and your data set, and nobody knows. But numbers that people use, so in general, people always use batch sizes of the powers of 2, because memory sizes are always powers of 2 and so on. So powers of 2 are good for the computer or for the graphics card architecture. And people pick something, for example, like 64, 128, 256, maybe even 512. Pick some. I don't know which one to pick, right? So I know what it does, the batch size, but I don't know which one is the best. And I think if you don't have a graphics card and you're calculating everything on your CPU, it basically doesn't matter much, I would say. I'm not sure. But if you're calculating your gradient descent on the CPU, it will be super slow anyways, right? So, you can experiment with different batch sizes. Oh, and then, can anybody say what an epoch is? We had this. We also have to specify the number of epochs. Does anybody know what an epoch is? Yes?
It's the number of time you do the iteration over your layer system?
Yeah, it's the number of times that you iterate over your entire training set. So if your training set is this is your entire training set, yeah? And now you split it into mini batches, for example, like this. These are now your mini batches. All the mini batches are always the same size, right? And then you do, during the gradient descent, you will first do one gradient step on this mini batch. Then do gradient descent on that mini batch, and then you do gradient descent on that mini batch, and this, then this, then this, and this. And when you're here, you start over again. Then you do another gradient descent step on this mini batch, and then this again. And one go over the entire training set is one epoch. So the number of epochs is how often do you iterate over your entire training set? So this is one epoch. So if you say that you want to train for 20 epochs, it means that you split your training set into mini batches, and then 20 times you go over your entire training set. So the number of gradient descent steps that you take is the number of mini batches times the number of epochs. Okay. I hope we have time for another example. Yeah, we definitely have time for another example. So until now, we only did classification, but a neural network can also do regression. And one thing you shouldn't, logistic regression, it's a bit unfortunately named because logistic regression is not a regression algorithm. Logistic regression is a classification algorithm. Regression is more like linear regression where you predict a real number. So in classification, you predict a category, and in regression, you predict a real number. So you predict, I don't know, 246 or 247. And the examples that we will look at is predicting house prices in Boston. So let's open a new notebook. So let's look at regression, predicting house prices in Boston. We need TensorFlow. Oh, you don't see anything, sorry. Import TensorFlow as TF. Let's predict the Boston house. Let's import the Boston house price dataset from TensorFlow.keras. Datasets import Boston housing. Let's import Matplotlib. Matplotlib pyplot as PLT. And models and layers from Keras. From TensorFlow Keras import models. And layers. Okay, let's load the data. Train data, train targets, test data, test targets as Boston housing load data. Oops. Okay. Train data shape. So we have, in the training data, we have very few examples. We have 404 districts in Boston, and for each of the districts we have 13 variables that we know. And in the test data shape, in the test data there's 102 examples. So the train targets are these. These are just the median house prices in different districts of Boston. So in this district, the median house price was $50,000, which sounds very cheap, but I think it's from the 70s. So back then, $50,000 was a lot of money. Okay. And now there's something that you should be careful when you prepare your data. Let's look at the mean value for each of the categories. So we have the 13 categories, right? And the categories are like how many, I don't know, something oxides in the air, and how high is the crime rate, and how many rooms do the houses have. And if we look at that, I mean, we average over x is 0. Then we see that category 0 has a mean of 0 point something, and category 9 has a mean of 4,000. Does anybody... So this is a problem. Does anybody have an idea why this is a problem? Yes?
I think the neural network would have problems with the scaling.
Yeah. So if our different variables are on completely different scales, right? The one is around, I don't know, 400, and the other one is around 0.01, then our cost function gets a very elongated shape, and our optimization will take forever because you get this. So say if our different features have very different scales, then in general our cost function gets a very not nice shape, and then if we look at the gradient here, it goes into that direction, right? So our optimization will do this. So one obvious, does anybody have an idea what we can do about that? Yes.
Yeah, we could normalize them, like.
Yeah, normalize the input features, like subtract the mean and divide them by the standard deviation. So everything is between is around 0 and with the standard deviation of 1. Okay, so let's normalize it. Or maybe we can first look at the standard deviation. Standard deviation is train data std axis 0 plt plot std. Okay, so the means are very different for each of these, and also the standard deviations are very different for the different features. So let's standardize the training and test data. Train data. Let's subtract the mean from the train data, and from the train data, let's divide it by the standard deviation. Now what do we do about the test data? We standardize the training data. What do we do with the test data? So for each of our training examples, we subtract the mean and we divide it by the standard deviation of the training set. But now, after we have trained the neural network and we want to apply it to new data, right? What do we do with the new data that we see? Yes?
I guess formally you have to normalize them as well, but for their own mean and for their own standard deviation.
Yeah, but if you say you have your trained neural network, you take it out to the world, you get a single training example. You don't know the mean and the standard deviation of the new examples that you get, right? And formally, you're also not allowed to leak information from the test set into your data processing, right? So it's very important that you subtract the mean and you divide by the standard deviation of your training data set. So you take your training data set, you take the mean and the standard deviation, you build a preprocessor of data for that, and you apply the same preprocessor for data for your training and then also later for testing. So the preprocessing of the data somehow becomes part of your neural network, right? Okay, so for the test data, we also subtract the mean of the training data set, and we divide it also by the standard deviation of the test data set. And then afterwards, when you go and tell somebody this neural network that you've trained, then don't forget to deliver them a function that standardizes their data before your neural network processes it, right? It becomes part of the pre-processing of the neural network. Okay, now let's look at the mean. Train data mean axis 0. Okay, now the means are very close to 0, right? I mean, it floats, so it's not exactly 0, but it's very close to 0. And then there's also one trick that you can do, is you have to, one issue is that every time you fit your model, you should build a new model. You have to be a bit careful. Every time you fit your model, you have to build a new model before that, because otherwise it will keep on fitting on the weights that it has fitted before. So in order to reinitialize all the weights randomly, you have to create a new model. And usually it's very convenient to build a function that does exactly that. So I can recommend you to build a function that builds a model for you. Def build model. model is, let's go for sequential. Model add layers. So we start with the dense layer. Does anybody know what the input shape is? Yes? Number of features, which is 13. So 13 features. How many neurons in the first layer? Yeah? More than 13. Okay, let's go for 64. Layer stands 64. Activation. What activation function? Let's go for ReLU. We always use ReLU. And the input shape is train data shape. So just the first dimension of the training data. This, yeah, starting at the dimension number 1. So the second dimension. Okay, let's add another layer. Model add layer stands 64. Activation ReLU. Okay. Oops. Model add layers dense. How many neurons in the last layer? Yes? Okay, and now the critical question, what activation function in the last layer? We want our model to predict the price of a house. So we wanted to predict something between, we want to predict it to predict a real number, right? What activation function will give us any real number? So the last layer will calculate W transpose X plus B, right? So what function do we put around that so it gives us something between minus infinity and plus infinity? The answer is nothing, right? We just take this. We don't put any activation function. We just take this, and this gives us some bias and some slope. So it gives us just a real number, right? We could put ReLU, because house prices can never be negative. But we can just skip the activation function. So one neuron, no activation. Okay, then model.compile. Optimizer RMS-prop as always. So now the question is, this is a regression function. What loss function do we use for a regression problem? Can we use cross entropy for a regression problem? No, we cannot use cross entropy, right? Because our results are not between 0 and 1. Can we propose any other loss function? Yeah. Mean squared error. Very good suggestion. Let's go for mean squared error as a loss function. And then as a metric, let's store mean average error. Okay. Then let's split our data into validation and training. Val data is train data, the first 300. Val targets is train targets, the first 300. And partial train data is train data, the rest. Oh, the validation set are from 300, the rest. And the train data are actually the first 300. So partial train targets, train targets, the first 300. Okay, now let's build our model. Model equals build model. Oh no! Okay, our notebook has crashed. Let's shut down a few notebooks. Oh, that worked. History is model.fit, partial train data, partial train targets, epochs. Let's go for a lot of epochs because we have so little data. Batch size 32, validation data, targets. Model is build model, model.fit. Oh, I think we should probably return the model, right? Oh, that was return model. Okay. Okay, we're done. Let's look at the loss values is history loss, loss values is history val loss, PLT plot loss values label training loss and loss values label loss PLT legend. Okay. Oh, it seems that we don't get any overfitting, right? So the trading loss goes down tremendously. The validation loss also goes down quite a bit. Then we can spend the last minute on evaluating the model. So, means validation mean squared error. Oh. Mean squared error, mean average error are equal to model evaluate on the test data, test targets. So the mean squared error is 20, and the mean average error is 3000. So now we built a neural network that can predict the house prices in the average house prices in an unknown, or the median house prices, sorry, in an unknown area in Boston from the crime rate and the, I don't know, the amount of carbon monoxide and so on in the air, with a mean average error of $3,000, which is quite good, I think. So we built a neural network that can tell you how expensive houses in your new neighborhood will be. Okay. So if you want, you can play a bit around with that, try different network architectures and so on. Next lecture, I can answer questions about the exam. So if you send me via email questions until Friday, I can answer or try to answer them next week, and otherwise we will just finish this neural network part, deep learning part, in the next lecture. So thanks a lot and see you next week.